Okay, so yesterday we looked at the importance of representing analog information into digital form and then communicating this information in digital form, right? Because we argued that if we do things that way, we are able to perform much better in the presence of noise than if you were to just transmit the information in the analog form, right? Of course, the key to this better performance is the use of repeaters, regular regenerative repeaters, which at intermediate points will clean up the signal and retransmit the cleaned up signal, and that's the reason this benefit of improved performance accrues if you transmit digital information rather than if you transmit the information in the analog form, right? So the issue then arises, how do you convert your analog information which you want to transmit into digital form, right? And towards the end of our course, we are basically going to discuss two techniques which will convert analog information into a binary digital representation, right? Which is something you may already know in the context of A to D converters, but we will look at it from the communication theoretic point of view, right? Now, one of the techniques which is extremely simple to implement to do this is what is called delta modulation, right? So it is not a modulation in the usual sense of the word. That is, you have a sinusoidal carrier and you embed your information onto the sinusoidal carrier. But yes, it is also even in the usual sense, it is a modulation, because the carrier here, like in other pulse modulation schemes that we discuss, is a train of pulses. So in that sense, it is a modulation because you are modulating a train of pulses, right? But the modulation is simply binary in nature. But the primary purpose here of this modulation is representation of the analog information into digital form, right? So delta modulator essentially converts or you can say encodes any message signal into binary form, into a sequence of binary digits. Or binary symbols, whatever you like to call it. These binary symbols are then represented by a train of positive or negative impulses, and that is how they are transmitted, right? That is, of course, the ideal picture. The practical picture will be that these impulses will be replaced with pulses of suitable duration, right? So these are represented by impulses of positive and negative polarity. The basic advantage of a delta modulator is that its modulation circuits and its demodulation circuit are extremely simple as compared to the conventional analog to digital converters, which you probably would have read something about in your maybe digital electronics. I don't know whether you read that, but if you have not, then you will read about it. But they are much more complex as compared to the circuitry of a simple delta modulator, right? Of course, there are some pros and cons to that, but we will look at that separately. So let me draw the block diagram of a delta modulator. It looks like this. You have the message signal coming in. Let's call it M of t. This is compared with, in a comparator, a reference signal which I will call M sub st, right, which is essentially some kind of an approximation to MT, which is reconstructed from the delta modulated signal from the final output. So there is going to be a feedback loop here. This reference signal comes from a feedback path, right? You will see what that path is. So you look at the look at these two signals. So basically, you have a comparator. You subtract these two. So what you get here is the difference between MT and M sub st, right? If the difference is positive, you generate a positive output. If the difference is negative, you generate a negative output, and to do that you have to have a limiter. So we have an amplitude limiter, right, which clips the output. If it is a positive signal, it will make it a plus, let us say plus 5 volts or plus 10 volts or plus 15 volts, whatever fixed value, let us say plus 5 volt, and if it is a negative output, it will convert into minus 5 volts. So basically the output, difference output information is encoded into a binary form, right. You are only looking at the polarity of the difference, not the actual value of the difference. Is that clear? Whether the difference is positive or the difference is negative, whether MT is more than MST or MT is less than MST. That's all you are looking at. This signal, this is a kind of quantized representation of the difference, a very crude quantization, where the quantization produces either a plus 1 or a minus 1, right. If the difference is positive, it produces a plus 1. The difference is negative, it produces a minus 1, and I am representing this quantized difference signal as delta t, right. This now, and this is where the modulation comes, this modulates or multiplies a pulse train, and for the moment we will take this pulse train to be an impulse train for mathematical convenience, right. So here is a pulse generator. So this is your carrier. So in this sense there is a PAM going on here, pulse amplitude modulation, but the pulse amplitude modulation will lead to pulses which are either positive pulses of fixed amplitude or negative pulses of fixed amplitude, positive impulses or negative impulses of fixed strength. Is that okay? And that's your delta modulator output. So if you were to call the delta modulator output as let's say x, your carrier is here, there is some carrier C, x sub Ct. This pulse generator gives you a train of pulses like this, impulses delta t minus nts. So there is a pulse rate involved which is 1 by ts, right. These impulses are coming, so the pulse generator is producing these impulses at a rate of 1 by ts, right, and therefore this signal x sub Ct is going to be essentially delta t multiplied with this impulse train, which is delta t minus nts, which you can write as delta t, or you can take this delta t inside and write this as delta nts into delta t minus nt sub s, right, because when you multiply delta t with delta t minus nts, obviously using the shifting property of the impulse function, you can write like this, right. Now this is a demodulator delta modulator output. You now have a feedback path which simply has an integrator, right, and the output of this integrator is precisely this reference signal MST. So the reference signal M sub st is generated from the delta modulator output by passing this output through integrator, and that generates your MST, and that completes the loop, and that's your delta modulator. This block diagram represents the delta modulator. To see what is happening in this modulator, delta modulator, what precisely is the kind of output that you get here, and how what it is doing, and also to understand it so as to then see how we can recover the signal from the delta modulator output. To understand all this, let us take a picture which shows precisely what happens for a typical waveform.
So we are only capturing the fact that how many bits are being used to encode one voltage level.
Only one bit is being used to encode one voltage level here. As you can see, all I am doing is taking the difference and encoding this difference into either a positive impulse or a negative impulse, single impulse, right. So it's in that sense a one bit quantization, right, single bit quantization in that sense. If you are looking at in the A to D converter context, it is different. You don't use multiple number of bits for each sample. You use a single pulse for, or single level, or actually binary level for representing each value of the difference signal. Okay, so x sub c, let me just make a comment here. This is a series, as you can see, the nature of this signal. Can you see what is the nature of the signal? It's just a series of positive and negative impulses, right? Isn't it? Because depending on whether delta, what kind of value delta t has, the output impulse will be either positive or negative. So final output is a digital stream, a binary stream, a two amplitude, two valued stream. And that's what you wanted. You wanted a binary stream. You got a binary stream. From this binary stream, you are generating this reference signal MST. So we need to understand what is the nature of this reference signal to understand what is happening, right? So this x sub ct is essentially a series of impulses with positive and negative polarity or negative polarity, depending on the sign of this difference signal. If I call this difference signal d of t, delta t is a quantized version of d of t, right? Now let's look at the reference signal. Reference signal is being generated from this signal, right? Isn't it? How? By integrating this. When I integrate this kind of signal, what will you get? This impulse will become a step function, right? So m sub st. So let's look at the reference signal. Here m sub st, the reference signal, you can write like this. It's delta nts. It is a sample value of the nth sample of d of t, and integration of delta t minus nts dt. Or I should use maybe a different variable. Let me call this alpha, delta alpha minus nts d alpha, which you can write as delta nts into ut minus yes, I think we can say that, right? Now can you physically picture what is happening here? You are basically creating a staircase approximation to the message signal MT. Can you see that? Okay, if not, let's draw a picture. Let us say this is your signal, right? This is your message signal MT. And here I will draw the modulated signal x sub ct. Let's assume for the moment that, as you can see, in any subinterval of t sub s seconds, the value of MST is going to be constant, isn't it? It's basically a step that comes in. Sorry, where is that? Yeah, a step that comes in, and that step will, the value will remain constant till the next step comes, right? Let us say in the beginning you are somewhere here. The reference signal was looking like this. So this was your MST, right? And let's look at this point you are comparing MT with MST. So MT minus MST is negative, right? So this negative, the quantized value of delta will become -1, and that will produce at the delta modulator output a negative impulse. That negative impulse, when it gets integrated, will produce a negative step, right? So basically what it means is that MST will go through a negative step. Is that clear? Let me repeat it if required. This was less than this, so this was negative. After limitation, this becomes -1. This produces a negative impulse. This negative impulse, after ts seconds, at this point is this time instant it produces a negative step, right, after integration, and that negative step now modifies the reference signal from here to here. Is that clear? And now this value will be held constant till the next pulse point, till the next impulse, till this changes. Now at this point what do you find? That MT is more than MTS, MST. So you will get a positive, D of t will be positive. Now you will get a positive pulse. Of course, don't go by what I have drawn here. So at this point, let me show, you are generating a negative impulse which led to this negative step, right? And at this point, you are generating a positive impulse which generates a positive impulse, right? And then at this point, that positive impulse generates a step in the positive direction, in the upward direction, and now this process repeats. Now what happens at this point? You will generate a negative impulse again, right? Isn't it? If you compare this and this, you will get a negative step, and you will reach here, then here, right? And so once again, so this was positive, this is negative, this is also negative. At this point, you are still negative, right? At this point, you will generate a positive impulse, and so on and so forth. I am not drawn a very good picture perhaps. So that is a sequence of binary impulses that you will get. And of course, this is a very crude picture in the sense that I have taken this step size to be very large, right, and this sampling interval to be rather large. You can make the sampling interval rather small and the step also rather small, and then as you can see, this picture will more or less approximate closely the actual waveform that you are looking for. Yes, please.
So isn't there a loss of information in this case?
Yes, there is loss of information.
So if the time interval in which we take these samples is during that time interval, if the MT changes by a large amount, then you cannot map the amount of change in MT. You
So I will
change either positive or negative.
we'll discuss all these issues. Just let's go through the process of understanding first. You are right, there is a loss of information. Any process which will represent analog information into digital information, there will be some loss of representation, loss of information in that, right? Only thing is we like to make that loss as reasonably small as possible, right? And we will have to see under what conditions will that happen. Those are the things we need to understand. But let's go through the process first. You are absolutely right. Okay, so is the process understood? This is how the delta modulator works. So basically, the reference signal is a staircase kind approximation to the actual signal, and in this way you generate a series of positive and negative impulses, right? And from this description, it is also obvious how we should demodulate. Well, how we should demodulate? Just pass it through an integrator, because that will produce a same staircase approximation of the receiver. Whatever we do in the feedback part can be done at the demodulator to produce a same staircase approximation to the message signal M of t. Only thing is, it is a kind of crude approximation, and if you want to remove those steps, you should pass it through a low pass filter to remove the high frequency components which are present in the edges of the step functions. Is that clear? So the demodulator will essentially be the same as this, that is, you have an integrator followed by low pass filter. So that is your demodulator. Really very simple. Any questions so far? Right. Now let's see the difficulties with it. There is one, of course, there is a difficulty of approximation. That is, you are losing information, right? But this loss of information may be insignificant if, for example, your step size is very small and your sampling interval is also very small. But in practice, you cannot make both these things indefinitely small, because if you do that, what will happen? If your step size is too small, you will see there are some disadvantages. But if your this pulse interval sampling rate is too large, right? You are obviously having to transmit information at a very large rate. Your rate of information transmission will become very large, right? Is that clear? So we don't want that also, because that is in a way going to use more bandwidth, right? So there are those pros and cons. But if you forget about these two issues for the moment, there are some other problems also with it, if you can look at it carefully. One is okay, let me illustrate. Let me also give it a nod. So let's look at two difficulties which are associated with the delta modulator. One is called slope overload. Okay. Suppose your message signal is changing rather rapidly. Okay. Now there can be a situation that this staircase approximation is not able to track the rapid changes that are happening in the message signal. Every t sub s seconds, you are increasing or decreasing this staircase approximation by a step size. Let's call it s. Okay? You are increasing this value by s. So suppose your signal was only increasing. Let's just for the sake of discussion, suppose your signal was only increasing at a certain rate. What is the maximum rate at which you can at which the staircase approximation can attempt to follow that rise? Maximum slope of this rise would be s by ts, right? You cannot have a staircase faster than this, right, which is dictated by two quantities. One is the step size s, the other is the sampling interval ts. So that is the maximum rate at which your signal can be allowed to rise. If your signal happens to rise suddenly like that, right, you will not be able to track this sudden change in the signal, right? So if during any time interval the slope of your signal increases beyond the maximum slope that the staircase can take, right, there will be the so-called this effect, slope overload effect, right? So this occurs when MT has a slope which is greater than what can be followed by a staircase approximation. As a worst case picture of this, suppose your message signal suddenly it's a step function, suppose it's a worst kind of situation. There is infinite slope here, right? So your staircase approximation was going perhaps like that, right, and beyond this it can only go like that. So you have totally missed this step. You can only go like a ramp, you cannot go like a step, right? And clearly the maximum slope that you can tolerate in the message signal is s upon ts, where s is the step size. Basically it will be dictated by the amplitude of the impulse that is coming in, isn't it? The strength of the impulse, and you can increase or decrease it if you wished. It will depend on the strength of this impulse. You can increase or decrease it if you want. You can put an amplifier here, right, to increase or decrease its strength, right, but usually it is kept fixed. So that's one problem with the delta modulator. Is it clear? In particular, suppose let's discuss this issue for the case of a I discussed this already discussed it here for the case of a step signal. What happens? Suppose instead of a step signal you have a sinusoidal message, right? Then that is your message signal is of the kind A sine 2 pi FMT. All right. Then what is the maximum slope that you can have? What is the maximum slope that this can have? Two pi AFM, right? So what is the required condition that for this sinusoid we never face the slope overload condition? We must have S by T sub S not much greater than, but greater than or equal to 2 pi A F sub M. So if you want to avoid slope overload, you should satisfy this condition for a sinusoidal message. So as you can see, for higher frequency messages, right, the slope overload is more likely to happen than for low frequency messages. But fortunately, as you know, typical message signals have a very interesting property. For example, the voice signal, the amplitude of higher frequencies is typically smaller than the amplitude of the low frequencies, and it is the amplitude and frequency together which dictate the slope overload condition. So it is the product of A into FM which will be important. So for voice signals, for example, it is sufficient if you satisfy this condition at some pre-chosen frequency, right, where the amplitude has a certain level which is typically known to be large, right. So for example, the reference frequency that is chosen to avoid this condition for voice signals, actually voice signals have many frequency components. It is not a sinusoidal signal, but just as a design method, you typically choose FM to be in the neighborhood of 1 kilohertz, although your actual voice signal goes up to 3 kilohertz or something, 3 or 4 kilohertz, right. So you have to ensure that the slope overload does not occur here. And excuse me, can you please shut this off? What was happening there? This is a class going on. Ribin, what was the problem? What was the sound? I don't know why you people do this. This is a recording going on. Okay, let's proceed further. Alright, so let's basically the point that I was making was that for voice signals we try to satisfy this condition at some fixed frequency within the voice band, which is typically 1 kilohertz, right. This just as a remark I am making for the design, from the design point of view. It is not important from the theory point of view. Okay, this is one problem with the delta modulator, the slope overload situation. The second one is, suppose your signal varies too slowly, right, very slowly it varies, or the amplitude of variations is very small as compared to the step size, right. Now let us see what will happen. The alternate steps will be positive and negative, isn't it? Now when you pass this through a low pass filter, what will you get? You will get a constant value. The average value of this positive and negative steps, which is what a low pass filter will produce, right, will be a constant value, and you will not be able to track these variations again. So very small amplitude variations also will get killed if your step size is too large, right. So we have two opposite situations. If your step size is too small, we are in the danger of having a slope overload condition. If you want to avoid slope overload, you must have the value of S to be large. If S is too large, you have the danger of facing this situation, that very small variations will not be able to track them. This kind of situation is called a granular noise situation. right. So, so either we have a slope overload situation if the step size is too small, or we have a granular noise condition when the step size is too large, right. So, you have to choose a value which is a compromise between these two conditions. So, this happens when S is too large and therefore unable to track very slow or very small variations, small amplitude variations. So, Venkat, is that okay? Have you got the answers to your questions? So, what can we do about these two problems that we have in the case of delta modulator? Can you suggest a solution? Some obvious solution from which follows from the discussion we had so far. Any other solution? The key lies in the step size, isn't it? When we want the step size to be large under certain conditions, and we want the step size to be small under certain conditions. So, if you are able to monitor what kind of conditions exist with the signal, and if we are able to modify our step size accordingly, right, then perhaps we will get a good representation of the signal. So, we need what is called an adaptive delta modulator, which is able to track the changes that are happening in the signal and modify its parameters to make sure that we continue to produce a good representation, right. So, that is the solution. So, we can have, so the solution to this problem is go to adaptive delta modulation, or go for adaptive delta modulation. Okay. And so, basically what do we want to do in the adaptive delta modulator? We want to be able to, we want to find out what are the slope conditions like. If the slope of the input signal is rather large in a certain time interval, you like to make sure that the step size is increased. If on the other hand the amplitude variations are very small, we should like the step size to be decreased, so that we are able to track this fine, right. That is what we want to do. So, how can we do that? How can we find out? Is it possible to find this out from the delta modulator output, you think?
If you have a continuous stream of one
Look at this condition. This is a typical slope overload condition. What would the delta modulator output in this condition? This MT minus MST is always positive during this entire interval. So, you will get a constant stream of a continuous stream of positive impulses at the output. So, if you get too many positive impulses one after another at the output of the delta modulator, that means that indicates that is a symptom of a slope overload condition, and we can do something about that. On the other hand, if we face this situation, we will always get a positive impulse followed by a negative impulse followed by a positive impulse. Alternate impulses will be positive and negative. So, if you get a continuous stream of positive and negative impulses alternating, that is a symptom for the granular noise condition. So, we can monitor these two conditions by the nature of the output of the delta modulator and immediately try to take some corrective action, right, and that is the principle of the adaptive delta modulator, right. So, if you keep that in mind and then you look at this picture, it will start to make sense. So, you have this comparator, this reference signal, this limiter as before, everything is same as far as the forward path is concerned, nothing changes. This is a pulse generator, there is an integrator. So far everything is fine, but before you feed the input to the integrator, how do you modify your step size? You can modify your step size by having an amplifier there, right, which modifies the strength of these impulses, right, or the amplitude of the pulses that are going there, isn't it? So you can have an amplifier. Only thing is, this amplifier has to be a variable gain amplifier. It cannot be a fixed gain amplifier, right? It was fixed gain amplifier for the normal delta modulator, right? So there is a variable gain amplifier here, variable gain amplifier, and this variable gain amplifier, the gain is controlled by a control signal. So this is not an input to a, this is not the input which gets amplified. This is a control input which dictates the gain of the amplifier, right? So this array that I have shown here is a control signal. This control signal will modify the gain to be large or small, but of course the signal that has to be amplified is this signal that is coming in, the feedback signal, right? This control signal has to be now generated from the, by looking at the delta modulator output. Is it clear? And one very simple way of doing this is just pass it through a low pass filter, this signal through a low pass filter, followed by a square law device. Sorry, I made it too small. A square law or a magnitude device. See what is happening? What we are saying is, if there are too many positive impulses or too many negative impulses coming in a row, right? So either we have a large positive slope or a large negative slope. So what will happen? What will be the low pass filter output? The low pass filter output will show a continuous, let's say, if you have, let's say, a large number of positive impulses coming, the average value will be some large DC value, isn't it? Average value over a few impulses, over a few pulses will be some large positive or negative DC value, depending on whether the slope is in the positive direction or in the negative direction, right? So we just need to monitor that value. So just pass it through a low pass filter, which will average out this positive sequence of positive. See, there is a sequence of positive pulses, right? There is a DC value associated with that over some fixed time interval, a constant average value. You look at that average value. If that average value is, magnitude of that average value is large, you decrease the gain. So this, if this control signal has a large voltage, this variable gain amplifier should be designed to produce a large gain. You want to produce a large gain. You want to increase the step size, right? On the other hand, if you have this situation of positive and negative impulses coming alternately, this control voltage will be, this low pass filter output will be small, and what you want now is this control signal should decrease the gain so as to keep the step size small. So that's the principle, right? Of course, you can implement this control logic also using an appropriate digital logic rather than this analog circuit, right? For example, you can actually have a digital logic which can track whether a few successive pulses are of the same sign or different sign, right, and produce a control signal based on that. So this can be replaced by a suitable digital logic as well. If you do things, let me complete please. If you do things like this, this particular kind of adaptive delta modulator is called a continuously variable slope detector delta modulator, CVSD delta modulator, right?
So what's the full form?
Okay, full form is continuously variable slope detector CVSD, right? Yes.
So can you explain this one again, that when is this too many pulses are detected on XCP? Greater than positive.
Yeah, because we get a large number of positive pulses. Let's say 3 or 4 successive positive pulses. during that time interval, see what does a low pass filter do? It basically carries out some kind of an averaging operation over some time interval. If you look at the if you look at the impulse response of a low pass filter and then look at that convolution operation, essentially it is some kind of an averaging operation that you do over a short interval of time, right? And that over a short interval of time, if a few positive pulses come, it will produce an output which is average of these values, right? Roughly, I am just roughly describing the effect of the low pass filter. The precise action will be governed by the precise nature of the low pass filter, right? So if this happens, you will get a reasonably large average positive value, and that serves as a signal to the amplifier that I must increase the gain.
So that the steps will increase.
So that, and the gain increases means the step size will increase, right?
So wouldn't it be better if you were to take the control before the limiter, from before the limiter? Then actually we know the difference between EMS and EMD. So we can yes, you know the difference.
The point is, it is best to work with something. Okay, I think it is a very important question. What is the other advantage of this way of doing things, rather than the way Venkat is saying?
Modular. Modular.
No, very simple. Remember, this is also your demodulator, isn't it? Here is a and this will now approximate the message waveform much better, and this approximation is being derived from the delta modulator output, right? So your feedback part, whatever it is, also becomes a delta demodulator. Your demodulator circuit now becomes this. So did you get the answer to your question?
Yes.
That is why we would rather derive this information from the delta modulator itself, so that whatever I am doing here becomes my model for what I should do at the demodulator. Is that clear? So it's a good question that you asked, and the answer is this. I was coming to that anyway. So your demodulator circuit is precisely this feedback path, because this feedback path is essentially reconstructing that message waveform for you with a better approximation because of the variable step size. Alright? Good. One last concept in the context of delta modulation is a very important variation of delta modulation, which is called sigma delta modulation. So these are very interesting terms, delta and sigma, and right, and these are as you can see, the circuitry is extremely simple, and all you need is a comparator, a limiter, and a, look at the circuit diagram. What are the kind of components you need? Adder, subtractor, a limiter, extremely simple to make. A multiplier in which one of the inputs is a pulse, extremely simple to make. These are very simple things to do. So that is why it's the delta modulator was a very popular method at one time, and it again has become very popular these days, right? All right. Now in the delta modulator that we discussed so far, if you just look at it purely from an intuitive point of view, suppose you were to roughly say what is the delta the X sub CT that you are producing, the delta modulator output that you are producing, what does it really represent? Does it represent the signal directly or indirectly? Indirectly. In fact, it represents the successive differences in the signal, isn't it? The positive and negative impulses that are coming, they are representation of the successive differences between the signal, whether the signal has recently increased or decreased from its previous value. Essentially, that is what it is able to monitor. So what is that? When you say successive difference, it's something proportional to the derivative of the signal, because the time interval is fixed, right? So in a way, the delta modulator output is a representation of the derivative of the message signal in a very crude sense, right? So in DM, the quantizer output, that is delta of t, you could say, based on this argument that I have given, is an approximation to m dot t rather than mt. So this is a very important concept. 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 This is a very important con Would you agree with this statement? Now, is that a good thing or a bad thing from the noise point of view? That is, if there is any noise, it will get enhanced, right? So, there is a transmission or disturbance somewhere, it will get accumulated because of the fact that the transfer function is omega square, right? Transfer function magnitude square is omega square. So, any transmission disturbance or noise in the system anywhere would lead to let us say cumulative errors. In the demodulated signal. Think about that. This, therefore, now how can we overcome this? We can overcome this by precisely using the same argument that we used to understand why this is a representation of m dot t. So, let us not try to approximate m dot t, let us try to approximate mt itself. How can we do that? Feed into the delta modulator not mt directly, but its integrated version, right? So, that is if you do that, that is what leads to a sigma delta modulator, right. So, and there are some addition. So, basically we can overcome this by integrating mt prior to delta modulation. And there are some additional benefits if you do that, because the low frequency components get pre-emphasized in the integrator, which is nice, and there is additional correlation between adjacent samples, and actually speaking, if you think about it, delta modulator exploits the correlation between adjacent samples, right. A good representation of delta, because successive differences, right. So, that correlation becomes much stronger now because of the integration, but those are things that I cannot spend too much time on it. So, basically a sigma delta modulator looks like this. You have an integrator and you have a normal delta modulator, right. And now tell me what will be a demodulator now. If I want to reconstruct this, I must have the integrator followed by the low pass filter, but I am not interested in this, I am interested in this. So, I have to differentiate the signal. So, integrator followed by a differentiator means I do not need to do anything, right. So, demodulator is simply a low pass filter, very simple demodulator. So, you still have a binary representation, everything is same, but you get both the advantages, a simplified demodulator and you remove that problem of being proportional to the derivative. Also, you can simplify this itself. If you think about it, this integrator may not be outside this plane. In fact, you see there are two integrators, one is here and here is the other one is here, right, and we are just adding here, adding things here. I can remove this here and bring in lieu of these two integrators, I simply have one integrator here, right, that takes care of both the things. So, my feedback path is simply a simple straight line. So, my final diagram of the sigma delta modulator becomes, are you with me? That is it, right. That is a sigma delta modulator. That is sometimes a simplified notation one uses for this, and the demodulator is simply a low pass filter. Okay, so we conclude our discussion on delta modulation here today. What I am not able to do about delta modulation, which I would have liked to do, is noise performance analysis of delta modulator. So that I am leaving as again self reading exercise. All right, thank you very much.